Okay, thank you for the introduction. Yeah, as said, I will talk about symmetry reductions in loop quantum gravity, a proposal which has been made last October. And the technical tool that we use to approach this is to perform a gauge fixing at the classical level and quantize in this gauge fixing. And this essentially corresponds to choosing suitable variables in which this problem can be solved in a very convenient way. And there are two papers on this. And there is one on the Bianchi 1 reduction, there's one on spherical symmetry, and this is in collaboration with Jurek Lewandowski and Jędrek Krzyzewski from Warsaw. So let me give you a brief outline of what I'm going to say today. I want to first give a brief overview of what people have thought about how to approach this problem of symmetry reduction in loop quantum gravity. I then want to discuss the general strategy, so what are the rules of the game that we're playing here, what are the techniques that we use. Then I want to discuss in detail the Bianchi 1 model because, well, it's actually quite interesting and it can be followed through in one talk. And then later, if there's time, which there's probably not, I'll give a brief sketch on how you do it also for spherical symmetry. So let's start then with the approaches. Now, the first thing that comes to your mind is, of course, to perform some mini superspace quantization. And I'm going to draw some picture now, which we will kind of add on during this talk. So what you always start with is GR up here, and then you want to reduce this the degrees of freedom there. And what you can do is you can, for example, go to Cosmology. And what we're going to consider here is, well, we're going to be using Bianchi 1 models, which means that the degrees of freedom on this side, they are three scale factors AI, which just tell you how the three areas of some Bianchi 1 universe is, and they also have momenta pi. And then, well, you can quantize this using standard methods, the Wheeler-DeWitt theory. However, we're not going to consider Wheeler-DeWitt theory here because it, well, has not been very successful. It did not resolve, for example, the Big Bang singularity. However, we're going to quantize this, as Aurélien told us on Tuesday, and we're going to go to loop quantum cosmology. And for those who don't know the details or don't remember the details, what is done here is the following. So instead of considering A and P as your canonical variables, you're considering A, and you consider the exponential of P. So you consider EI, some natural or some real number lambda, and then you put this P here. And lambda is in the real numbers. And then you say, well, you want to kind of probe those guys here, and you need to define a scalar product and Hilbert space and so forth. And what you will do is essentially your quantum states are these functions of P here. So it's going to be something like this. And you're going to introduce a scalar product, which is e to the I lambda P, e to the I some other lambda prime P. And this is just defined as delta lambda prime, where this is the Kronecker delta. It's not the Dirac delta. And the resulting Hilbert space is then just an L2 space, not over the functions on the real line, but over functions on the so-called Bohr compactification on the real line. So this Bohr compactification is just, well, it's also called the space of almost periodic functions. So this is like a plane wave, so it's a periodic function, or in this case called almost periodic function. You take all those functions and you complete them with respect to some norm, and then you arrive at the so-called space of almost periodic functions. And there is a measure here, which is the Haar measure on this space. And since, well, it's called Bohr compactification, which already suggests that in the topology used here, this space is actually compact. So it's a space which is larger than the real line. However, in the topology that is used there, it is compact, and there exists a normalized in translation invariant Haar measure on this space. So this is just what is done in loop quantum cosmology. So the only kind of difference to Wheeler-DeWitt is that you use these, what people call polymerized objects here. And you have a representation which is fundamentally inequivalent to the Wheeler-DeWitt representation. And in particular, it also avoids the von Neumann uniqueness theorem for quantum mechanics because the scalar product is not weakly continuous. Okay. So this is just a brief reminder of what is done in this loop quantum cosmology business, and then Aurélien told you what, for example, predictions are there. So then, of course, you kind of want to do the symmetry reduction kind of the other way around. You want to first quantize and then reduce. And there are various approaches for this in the literature. For example, the first thing that people tried is you could use some approximately symmetric quantum states. In our context, these are called spin networks. We, for example, heard on Monday by Jakubilski on this theory of quantum-reduced loop gravity. You could study this symmetric connections. I mean, we'll tell you later a little more in detail that what we consider in loop quantum gravity are spaces of connections. And then you can ask yourself what are symmetric connections there, what are measures supported in such connections. We also heard from Stefan Gielen and Daniel Oriti about condensate states and recent progress in group field theory on extracting a cosmological sector. And what you could also imagine doing is you could imagine that you find the symmetry generator of your symmetry transformation that you want to implement at the quantum level. And once you have this generator, you can group average with respect to this generator. And this can, for example, be done in spherical symmetry, as was shown in this paper. However, what I'm going to discuss today is yet a different approach, and it's the following. So we can classically code symmetry as the vanishing of certain phase-space functions which vanish in the symmetry-reduced sector. For example, in a Bianchi-1 model, the off-diagonal components of your metric and your momentum, they would vanish. You can then quantize your full theory. In particular, you quantize also those functions which vanish on this reduced subspace, and you define your symmetric quantum state as a state in the kernel of all those operators. And this is the strategy that we're going to follow through in this talk. You might imagine that in general that would lead to some intractable problem. However, the point here is that due to this gauge fixing that we're going to perform, the computation of this kernel will in the end be trivial if you know kind of the formal literature in loop quantum gravity. Okay. So, and in particular for this Bianchi-1 reduction, we're going to show the following thing. So what you want to do here, you want to go to some quantum GR, and then you want to reduce here. And the important question that you also ask in the end is, do these arrows commute here? Or more precisely, since you can construct many such arrows, do there exist arrows like this and arrows like this such that this commutes? And the statement that will be in Bianchi-1 case, indeed there exists an arrow like this, and we will construct it such that this actually commutes this quantization. And I will be more precise later in what I mean with that. So let's then start recalling the general strategy of what we're going to do here. So first of all, let me specify the rules of the game. So we're working here in the context of canonical loop quantum gravity. We've heard about different approaches before, about group field theory and spin-4 models. Here we're doing a Hamiltonian formulation of general relativity, and we quantize using the standard rules of quantum mechanics. So the thing, or which is basically mainly different to Wheeler-de Wit, is that we're not going to try to quantize in metric variables, but we're going to quantize in connection variables. So at the classical level, we're doing some canonical transformation, also a phase-space extension, introducing some additional gauge symmetry and constraints, and we're going to rewrite GR in those variables. And well, a priori, you can choose many such variables. In standard, you choose SU2 connection variables in 3+1 dimensions, called Ashtekar-Barbero variables, but you can also go to higher dimensions. And you can also think about how you can modify this construction also in 3+1 dimensions. But the point is that once you have such connection variables with suitable mathematical properties, being that you have a compact gauge group, you have real variables, they should have canonical Poisson brackets, and you might also demand that all your constraints are first class, so you can do a Dirac quantization. Maybe you can also lift this by doing some other type of quantization. So the point is that once these are specified, then there exist powerful mathematical methods, rigorous mathematical methods to quantize this theory, using, for example, the GNS construction and the theory of C-star algebras. And the statement is that once those are satisfied, there is a unique representation of this kind of algebra that you have here. The assumptions that you do is that you assume spatial diffeomorphism invariance in the sense that your representation should be spatially diffeomorphism invariant and also irreducible. And then uniqueness follows here at the kinematical level. So with kinematical, I mean you of course still have constraints that you want to impose, in particular the Hamiltonian constraint, and then on the Hilbert space that you derive here, you can regularize those constraints. There are several proposals for this. So the main rule that you follow there is you need to take the GR constraint, you need to express it in the variables that you have here. In particular, we're not really using the connection, but we're using finite parallel transports of the connection, such as those guys here. And then, for example, you need to approximate, for example, a curvature tensor by some finite holonomy, which you shrink towards a point. And then you want to do such a construction and take a limit such that kind of the regulator that you introduce is either removed, this is in the original construction by Thiemann, or that you're working on some fixed lattice, and that in kind of the continuum limit, also your regulator goes to 0. This is some later construction, which is not cited here now. So these are the rules that you want to follow. So you want to recover GR in the classical limit with such a construction. And then you can ask what are the options here, and you find, well, there are kind of many regularizations that you can choose a priori. However, there are strong constraints by, for example, anomaly freedom. And just to mention here, so in this first construction, it was claimed that you have an anomaly-free representation of the constrained algebra. So the precise statement would be that there's a certain on-shell sense in which this is anomaly-free, being that Hamiltonian diffeomorphism constraints are treated on different footing there, and there's a precise sense in which this is anomaly-free. However, people would generally not agree to call this anomaly-free. So if you, for example, look in the famous review of Hermann-Nicolai and collaborators, there it is questioned that this should be called anomaly-free. But then there's also more recent work going on by Varadarian, Lara, and collaborators. It's very, very interesting work in my point of view, and they really try to modify or kind of refine these regularization procedures here, such that at the quantum level, if you quantize those constraints, you really get a commuting algebra. And this has been shown to work in the case of the spatial diffeomorphism constraints with a certain regularization. There you find that there are some subtleties that were overlooked before. In particular, there are kind of higher order corrections which vanish in the continuum limit, and if you take them into account properly, then your algebra really closes at the quantum level. There's also more recent work on the Hamiltonian constraint in some simplified model, which is a three-dimensional kind of U1 cube theory, and there you can also get such a thing to work for the Hamiltonian constraint. But this is just to say that this dynamical part here is not worked out and agreed upon in the final stages, so there are many proposals. They work to a different extent. However, we can still try to define dynamics. And in particular, along this arrow, following one of these proposals, we find that we obtain the cosmological dynamics of loop quantum cosmology, which are in particular consistent with observation. Okay. So let me then discuss this strategy that we're using for defining this quantum reduction. As said before, a main point will be to use a gauge fixing, and we're going to gauge fix here the spatial diffeomorphism constraint. And so we're going to choose a gauge fixing which is adapted to the symmetry reduction we want to perform later on, in particular for spherical symmetry and for Bianchi 1, these will be different gauge fixings. But once you have specified such a gauge fixing, you can just follow standard procedure. You go to the reduced phase space of your theory, which means either you solve the constraints or you employ the Dirac bracket, which are equivalent procedures. And then on this reduced phase space, well, you have kind of less degrees of freedoms as before because you solve constraints. But since we're doing this loop quantization procedure, we still need to construct a connection. So we're going to take these degrees of freedom in the reduced phase space, and we're going to construct connection variables from them. And these are, of course, different than Ashikawa-Barbero variables because we have less kind of degrees of freedom to assemble in a connection. Okay. So then the next thing we want to do, we want to identify suitable functions which vanish in the symmetry reduced sector. So we're just calling them here f of some p and q, some generic functions. They vanish. Like a priori, if you choose such functions, they might be a first-class set or a second-class set of constraints, in the sense that, well, they might commute or they might not commute, or they form a closing algebra. And since we want to implement them in a Dirac quantization, meaning as strong operator equations, we need to choose a first-class subset of them. And there's a consistent procedure of doing that, which is known under the name of gauge unfixing. And well, the basic statement here is that if you have a second-class pair, you can view one of the constraints as a gauge generator, you can view the other one as kind of a gauge fixing, and then you want to have some consistent procedure of dropping the gauge fixing such that the theory is still equivalent, and this can be done, and how this is done is described in this procedure here. So then, having done this, we want to quantize the reduced phase space up here. Reduced just refers to the constraints, or one of the constraints has been solved. It's not reduced in the sense of symmetry reduction. So at this point then this is still full GR, at least if it's if this gauge fixing is accessible. Of course we know that generic gauge fixings are not globally accessible. However, at least in the space where such a gauge fixing is accessible, this is still full GR. And also there are no spatial diffeomorphisms anymore. There's a small qualifier because there might be some diffeomorphisms preserving your gauge. However, in the constructions that we're going to perform, this is not going to be relevant in the end, so you can just forget about this for this talk. Okay. In particular, for loop quantum gravity, this means that you do not have this constraint anymore at the quantum level, and you do not need to solve it anymore at the quantum level if you are in this full theory setting. So then, after you have done this quantization, you want to impose your reduction constraints. That means you build these operators f hat, and you compute the kernel of these operators, and you define those states to be your symmetric states. So you want to find this symmetric subspace. And then also you want to know what observables are acting on this space. That means you want to find observables that commute with your reduction constraints. And if you have such objects, of course, they will leave this space invariant. Okay. And then in the last step, what you want to do is you want to find out how do these observables correspond to these degrees of freedom which we have in the Bianchi-1 cosmology, and you want to study their dynamics from the point of view of the full theory. And then you want to compare to the dynamics that you find in cosmology. Okay, so let's start now looking at the details for how this can be done in the case of Bianchi-1. So as said, we are going to perform a gauge fixing for the spatial diffeomorphisms. We start with the usual ADM phase space. Q and P are canonically conjugate. We impose the gauge condition that the off-diagonal components of the metric vanish. So Q we just write as a diagonal matrix of QXX, QYY, and QZZ. And, well, this gauge fix is a spatial diffeomorphism constraint, at least most of it. There's some small set of shift vectors left invariant, but as said, this is not relevant for this talk. I display the constraint here just for one purpose, which is to later see that this constraint is linear in P. I mean, this will kind of give you some intuition why the result of the next slide might be true. And what you do now is, well, you choose coordinates on your reduced phase space. You just choose the diagonal components of the metric. You choose the diagonal components of the momentum. These still have canonical brackets. You solve the spatial diffeomorphism. You solve this constraint here by just setting those guys to 0. And now you need to solve the spatial diffeomorphism constraint for the off-diagonal components of your momentum P. So therefore, by solving C equal to 0, P off-diagonal will be expressed in the diagonal components of Q and P, and you can now take this guy and insert it in the Hamiltonian, and this will give you a Hamiltonian which stabilizes your gauge fixing. So this is just standard procedure, nothing is happening there. So there's one caveat here, which is that this leads to a partial differential equation for the lapse, essentially, for the shift vector, and this partial differential equation for this case of this gauge fixing cannot be solved in general, or at least I don't know a solution. However, this leads to some correction term in the Hamiltonian, which you would have here. However, this correction term drops when you take the 0. So if you want to compute the dynamics of the reduced variables here, then this correction term is kind of irrelevant for the study of the cosmological degrees of freedom. So we actually get kind of around here if we're just interested in the cosmological sector of the full theory. So then, having those variables, we now need connection variables. We're going to do a construction which kind of resembles the usual construction of vielbeins and or Ashika-Barbero variables. However, it's different. So what we're going to say is, well, if we take some diagonal component of the metric, we're kind of taking the square root. We're using this EA such that EA times EA is QAA without any summation implied. We can also construct an inverse EA, and we can also construct a densitized vector version of this EA. So this then resembles the kind of the triad of GR. However, the difference is it has no internal index. So there's kind of a single triad for each of these metric components. You can also define some object you call K lower A, which you define like this, the external curvature you get from the P. And what you find then is if you compute the bracket between K and E, you find it is canonical. So you might wonder about this construction because it's non-geometric. So here you take the square root of a component of a metric. You might be worried in the end that that you run into problems. However, you find that, I mean, these reduced diffeomorphisms that you have here, they still act as proper diffeomorphisms on those guys. And in the end, it will turn out that the reduction constraints that we are going to construct, they are going to act in a geometric way on those guys. I mean, this is a priori non-trivial. However, it will be the case in the end. But without these geometric considerations, we see, well, K and E, they look like Ashikawa-Berer variables. However, they are actually the variables of an abelian gauge theory. So they are, in particular, giving you the Poisson bracket of Maxwell theory. So we have done nothing else than having 3 plus 3 degrees of freedom here, and we made 3 plus 3 degrees of freedom here out of them and computed their Poisson bracket. And to emphasize it again at this stage, we have the Hamiltonian constraint left and only those diffeomorphisms kind of stabilizing the gauge. So this is still full GR. And for people, I mean, more familiar with loop quantum gravity, I mean, you would not impose some spatial diffeomorphism invariance on this phase space then. So this is the main difference between the usual loop quantum gravity. So now we're going to think about which kind of phase space variables vanish, or which functions vanish in the reduced sector. We're going to consider a Bianchi 1 universe on a 3 torus. So we have 3 scale factors and 3 momenta. The metric is supposed to be a diagonal. In such a model in particular, these components, they're independent of the spatial coordinate. So what we can impose directly is we impose that both Q and P, they are diagonal. We say here in suitable coordinates, because such gauge conditions always kind of select coordinates. So we actually impose that P A naught B is 0, which then translates to an equation on Q and P diagonal by this solution of P A naught B from the diffeomorphism constraint, and then this translates into a conditioning of K and E. We're also going to demand that both E and K, they are independent of the spatial coordinate, which we can, for example, say that their partial derivatives vanish. I mean, these are statements which are satisfied in the Bianchi 1 model, and we can, for example, demand them to find the reduced sector of the full theory. So the question is now, what are the first class what is a first class subset? And I cannot give you the details here because, well, of time reasons. But the statement is that a maximal first class subset is given by all spatial diffeomorphisms acting in those variables here, and the Gauss law acting in these variables here. So this is the Gauss law of Maxwell theory, and these are spatial diffeomorphisms acting on the variables of Maxwell theory. So that you, for example, get this Gauss law, you can imagine from here, I mean, you can reformulate this such that you can kind of make the Gauss law out of these guys, that you get all spatial diffeomorphisms essentially comes from the fact that the spatial diffeomorphism constraint is linear in P. So if you solve for certain components of this guy, you kind of take some components on the left-hand side. The remaining components, they still look roughly like a spatial diffeomorphism constraint. However, you find they're not quite the components of a spatial diffeomorphism constraint because, essentially, because of the non-geometricity in your construction here. However, you can fix this by such terms here, and yeah, what you find in the end, you have spatial diffeomorphisms and you have this Gauss law, and well, of course, those guys form a commuting algebra. So the result is that direct consequences of a Bianchi 1 reduction can be imposed as spatial diffeomorphisms and a Gauss law on the reduced phase space. And the strategy that we're going to follow is we're going to quantize well without reducing, and at the quantum level we're going to impose those two constraints and we're going to compute their kernel. And if you come from loop quantum gravity, of course you know it's well known how to impose such conditions since essentially this since about 20 years, and this is of course long ago. Okay. So let me summarize briefly what we have done. We have rewritten the phase space of full GR admitting this diagonal gauge fixing as in terms of 3 plus 3 canonical coordinates, which are variables of an abelian gauge theory. We had these remaining constraints here. We identified consequences of a reduction as those constraints here, and our strategy is now to quantize the full phase space and impose the reduction constraints at the quantum level. So let's do that. So now there comes the step of this loop quantization, which was argued before to be some mathematically rigorous procedure. So let me give you some more details here, what we do in this case. So here we have an abelian gauge theory, so it's kind of quite simple what we do. We said we do not consider kind of the K directly, but we consider holonomies of this connection here. So we integrate it along in some arbitrary path gamma, and we're going to exponentiate it, and we're going to multiply it by some number here, lambda. And a priori, you now ask, like, what do you want to choose for lambda? And if you kind of remember Maxwell theory, which is usually taken to be theory with gauge group U1, you would say, well, these lambdas have to be integers. However, there's also the possibility to take them to be real numbers, in which case your gauge group would be the Bohr compactification of the real line. And in particular, later it will turn out that this Bohr compactification is preferred for a reason that I will discuss in a few slides. Okay, but once you have specified this algebra, and you also say that, well, you consider fluxes, you integrate this electric field over any surface, and it's just the electric flux through the surface. If you consider this algebra, then there's a unique diffeomorphism invariant and irreducible representation of that, which is done by the Archicka-Lewandowski construction. So there's this functional on it. By the GNS construction, you get a Hilbert space. And well, in the end, again, what is this Hilbert space? This Hilbert space is just a space of the square integral functions on the space of connections, and then there's this closure here, so we call this the space of generalized connections, which is just, well, the space of connections closed with respect to the measure that we have defined here, and this measure is well, also called Archicka-Lewandowski measure, and follows from this GNS construction. It's very similar to what you have in lattice gauge theory, I mean, from the perspective of the measure. Okay. So then, just a remark for those who don't know the Bohr compactification. Again, it's kind of a compact space. There exists a normalized and translation invariant Haar measure, denoted by d mu Haar here. You can define it in the following way. So you just take an integral over some box surrounding 0. You divide by the size of this box, and you send the box to infinity. In particular, then you will recover such a scalar product here. So in particular, plane waves are normalizable in this measure. And then, just as a comment, choosing this lambda here to be in the integers for U1 over being in the real numbers, there's actually no a priori justification of this, because it corresponds to a compactification of this integral here. And we will later see that this would lead to dynamical problems if we actually compactify this. Okay. So let me then introduce an operator which is important. It will correspond to one of those areas here, which is, well, the area operator. There's a difference here to the area operator in loop quantum gravity, which I'm not going to stress kind of in the spoken word. It's written here, so for those familiar with loop quantum gravity, they will notice the difference. So here we just say, well, what we had here was kind of Maxwell theory. So in Maxwell theory, we have the electric flux through a surface, which is just, well, this electric field integrated over the surface. And yes, and you now check what this actually corresponds to in our variables, and you find that this just corresponds to the area of this surface. So it just gives you the kind of the area density derived from your metric, and it gives you the physical area of this surface over which you integrate this electric flux. Probably, yeah. Mm-hmm. Yeah. Not that I know. No. So yes. So you just have the area of some surface defined like this, and now you ask how does this guy act in the quantum theory? Now the quantum states, they are essentially. I told you that we compute holonomies along some curve here, for example, this curve here. So this path here is this gamma. It's with respect to some representation of your group. And then assume that you have a holonomy like this, and it intersects a closed sphere. So you will find that there are two intersections, plus and minus. They will cancel each other out, which is just a statement that if you have no charge inside some closed sphere, then there is no electric flux through the surface. The point is here, it works because both of these guys are contractible. So if you now go to some more general situation with non-trivial topology, for example, a 3 torus universe, the 3 torus is this box here, then, well, opposite sides are identified here. Then we can, for example, write this closed surface S here, which is just some sub-2 torus. And if we would, again, write a contractible loop here, then the surface of this guy would again be 0. However, if we write a non-contractible loop like this, running around one of the direction of our universe, then we get just a single contribution here, and well, we will get a non-vanishing area from such a state here. So, and what you just find is that this A, it just measures the intersection number times the representation label of such a holonomy. Because in particular, if you now take this guy and deform it, for example, to come back here intersect again and go here, then you would still get the same result because, well, it always measures the net intersection number. So, yeah. So this is this operator here, this area operator, how it works. And now let's just impose our reduction constraints. So we want to impose kind of spatial diffeomorphism invariance and Gauss Law invariance. So Gauss Law invariance is kind of trivial. You only consider closed loops here because we know that they're gauge invariant. Now the construction of this spatial diffeomorphisms essentially is an average overall spatial diffeomorphism. So there's a technical precise way to do this, which is more elaborate than just saying it's an average. And in particular in these measures that you use in loop quantum gravity, there's a precise mathematical sense in which this can be done. And you really get some state, which is not in the Hilbert space, but in its dual, but it is spatially diffeomorphism invariant. So we can work with such objects here. And that is, I mean, painting again our universe here, we now write the simplest state that we can think of, which is non-trivial and satisfies its properties. So we consider a holonomy running in x, in y, and in z direction. And, well, they are closed. We demand them to meet in one point, which is, I mean, not so important, but it's nicer. We have diffeomorphism averaged them. So the only thing that these guys remember is, well, they meet in this point, and they remember the direction in which they run. So this curve could be arbitrarily deformed by diffeomorphisms, and you have to think of it as a diffeomorphism equivalence class. But what the diffeomorphism cannot do is it cannot like switch this curve from here to here because, I mean, there's no continuous connection to do this. Yeah. So what we see here, we have kind of 3 topological degrees of freedom. And a system like this was already thought of by Vicar Hussain in the 90s, which he called topological quantum mechanics. So he thought about kind of embedding a finite quantum mechanics system into a field theory by embedding the finite degrees of freedom onto the topological degrees of freedom of the field theory. And this is essentially the picture that you will arrive at in the end. Let's say a second about this. So now you want to study observables with respect to the reduction constraints. You find that the 3 areas along these tori here, they are observables with respect to the reduction constraints. You can see that in the following way. Well, they trivially commute with the Gauss law because they only depend on E, so they commute with E. And they also commute with the spatial diffeomorphisms because you can arbitrarily deform this surface and it will again not change the net intersection number with this loop. So this is a kind of inverse argument of saying that you deform this loop here and it will only measure the intersection number. You can make a similar argument with kind of the holonomies themselves as being observables. And then, well, what is the information left here? The information left is just these representation labels on these holonomies running in x, y, z direction, which we call lambda x, lambda y, lambda z. And you can now map that directly to what people have considered in loop quantum cosmology, and they just call this state P1, P2, P3 in this paper by Ashtekar and Wilson Ewing. Yes. So there was already earlier work on this subject, but I choose this one because I want to kind of arrive at the dynamics which is defined in this paper on the next slide. Yeah. So now, last step here in this derivation, you want to look at the dynamics. So you take your Hamiltonian constraint, you rewrite it in the variables that you have. You kind of arrange it in such a way that there is kind of a Hamiltonian plus these reduction constraints, and you just say, well, they drop when I impose my reduction. This is not 100% clean because in the Hamiltonian and diffeomorphism constraint, they're currently treated on not equal footings in LQG. So there's, as mentioned before, there's work to kind of remove this problem. However, here they are not treated on equal footing. So if you actually have if you put a diffeomorphism inside the Hamiltonian constraint, you would not know how to regularize it in the full theory such that it acts as some finite diffeomorphism. So this is an open problem here. However, here we just say that if there is a way to do this, which you would hope, then they would just drop. On the other hand, you could just I can give you a way to regularize those additional terms such that they drop on this state which I showed you before, which essentially comes from the fact that if you regularize them according to the rules that were used before, then they would drop on this state because they always refer to kind of differences between neighboring vertices and the neighboring vertex of this guy is itself, and then you would always get some 1 minus 1 contributions to this constraint. So, but if you accept this for the moment, then essentially the Hamiltonian that remains looks like this. It's still an integral, but this looks like the Bianchi 1 Hamiltonian. What you then need to do is you need to express it in terms of these holonomies and fluxes. So you could either use Tiemann's trick and kind of rewrite these lower guys by a commutator of connection and the volume. But what you also can do is, and what you also need to do is, you need to substitute an integral over k by kind of the sign of this integral, and then you put this lambda here. So here we see that there might be a problem if you choose this lambda too large, because, well, the sign properly probes this guy only if this guy is small compared to this lambda, or kind of something like 2 pi over lambda, not bigger than that. And in particular, what you find, if you choose lambda to be an integer, then the best approximation is provided by lambda equals to 1. And then if you follow through this derivation, you find that the dynamics you get are the so-called old loop cosmology dynamics, which were defined in this paper, and they suffer from physical problems, so they do not lead to acceptable dynamics in accordance with observation. However, there's a way out, which is essentially to modify this prescription according to these new loop quantum cosmology dynamics. And the statement there is that you want to choose this lambda such that kind of 1 over lambda is the size of the universe, so that the representations that you choose here in your Hamiltonian constraint, they are kind of dynamically determined, and they're determined on how big your universe is. So you can imagine that as saying we want modifications only at Planck density. So there is a more kind of a better argument inside LQC to kind of arrive at this statement there, which is kind of different from here. Over here, we just say, well, in order to get a good approximation for the Hamiltonian, we kind of need to make this thing dynamically small. I mean, and the smallness needs to be determined dynamically. And then actually the simplest choice that you can make is this one here. It's just the size of the universe. So, I mean, from the simplicity argument in this case, you would arrive at this regularization, and then it turns out that this leads you exactly to the new dynamics for these operators. And in particular, I mean, these are fine with observation, as Aurélien told you on Tuesday. I mean, the catch here is that, of course, to compare to observations, you need to know how perturbations propagate on your quantum space-time. And this is not worked out in this reduction or in any other reduction so far. So there's something left to do, which is, of course, kind of compute how propagations or how perturbations are taken into account here. However, for the kind of zeros order problem for the homogeneous modes, you find that these two arrows, or there exist arrows such that they commute. Okay, so 12 minutes. That's very nice. So let me give you a brief sketch of how this can be repeated for spherical symmetry. So for spherical symmetry, you do the same thing, but you need a different gauge fixing. For spherical symmetry, you are using some sort of radial coordinate system. This is known in the literature under various names. It's known under radial gauge. For ADS-CFT people, it's known as a holographic gauge or Pfefferman-Graham gauge. It's also called axial gauge sometimes, or you can also call it a Gaussian normal coordinate. And so the idea is the following: you define some central point, and while I'm referring to this paper, I learned this from this paper, and the construction in this paper is, as far as I know, it's the first construction where the observable algebra in such a gauge has been computed explicitly. So people have thought about this gauge before, but this is the first paper where the observable algebra has been computed. And is correct, I might add. So there were other shots at this. So the idea is basically you define some point sigma 0. And so first I'll give you one version of this. You define some central point sigma 0. From this point, you shoot out geodesics under some angle and with some geodesic distance, and they then just define you a coordinate system. You just define it as the exponential function at this point, so where you shoot out the geodesic. Then there you can define these local angles and this radial distance, and this is just Gaussian normal coordinates. In particular, what this defines you are spheres of constant geodesic distance from your central point. So and this is of course nice for spherical symmetry, because in the end you want that kind of the state is kind of homogeneous on such a sphere of constant geodesic distance from your central point. You can also invert this argument and shoot these geodesics in from infinity. So this is what is usually considered in ADS-CFT. Okay, so in order to impose such a gauge fixing, we impose well, what we call radial gauge. So the metric has a form which is written here. So you kind of, this defines your coordinate system. There are kind of radial coordinates r, and then there are angular coordinates. And you want that, just write it here. So your metric is supposed to look like this. There's 1, 0, 0, and then there's some, and these guys are free. So the radial kind of components are determined by this gauge fixing, and the metric, this guy here, which is just the induced metric on this sphere, this is your dynamical variable. Now, well, what you find here, well, what do you have here? You have a 2 by 2 metric, so we just go to 2 plus 1 quantum gravity and take the connection variables from there. And we know that in 2 plus 1 quantum gravity, we can choose SU2 connection variables. We just call them A and E again. Now they have this internal SU2 index. The difference to Ashtekar-Barbero variables is essentially that these tensor indices then are now capital AB, which are just angular variables. So this connection is non-trivial only along these spheres of constant geodesic distance, and the flux, or the E, is only non-trivial if it's orthogonal to these spheres of constant geodesic distance, because you need, in order to integrate it, you contract it with an epsilon symbol, and then there's an RA here. So there's always a radial direction along of the surface along which you want to integrate this E. But well, you find that they're canonically conjugate. This is, as I said, nothing new. And now you need to do the same thing as before. You need to solve the spatial diffeomorphism constraint for PRR and PRA. This gives you an equation for PRA in terms of the reduced variables. Here, there's some kind of something funny happening. The partial differential equation that you need to solve to do this, it splits, and you can integrate it explicitly. So the explicit solution of that is provided in this paper here. And therefore, you can explicitly write down your Hamiltonian. Okay. So now we want to find again conditions which vanish in the reduced phase space. You just look into papers, for example, Kukash or so, then you find that the PRA, so the P radial angular components of this momentum are 0. You can also imagine this as, well, this is like a vector field on a sphere, which is supposed to be spherically symmetric, so it has to vanish. And, well, what you then find by looking at the solution of this equation, if you sample all PRAs, then this is the same as the generator of spatial diffeomorphisms in terms of those variables, preserving the spheres of constant geodesic distance from the center. So the statement here is you can impose spherical symmetry as invariance under S2R preserving the diffeomorphisms. And to stress it again, these are not the gauge diffeomorphisms that we had in GR. These are kind of active physical diffeomorphisms with respect to a physical coordinate system that you have chosen in the beginning. Okay, so now we again quantize SC2 gauge theory with use holonomies. This is the same as in LQG. The only difference is that the holonomies are now restricted to lie on those spheres of constant geodesic distance. So you don't have any holonomy running between those spheres, but only the spin networks embedded in those spheres. So you kind of have a hierarchy of like radially outgoing spin networks. And well, our quantum states are these spin networks. You can call them generalized Wilson loops. They have support of different on those spheres, but not in between two spheres. You impose the reduction constraints by going over to spatial diffeomorphism invariance on each S2R. So since we have kind of individual spin networks on those spheres, we perform the individual diffeomorphism average on those spheres. And now you ask yourself, what are observables with respect to those reduction constraints? Of course, I mean, you can write down those two here directly. The area of a sphere is, of course, a diffeomorphism invariant concept. So we just integrate the metric, so these guys here, the metric determinant square root over the sphere, and this is what people call 4 pi r squared in spherical symmetry. And we can also define the momentum to this r by, well, it turns out to be this guy here. So, and also again, it's spatial diffeomorphism invariant because it's kind of a proper integral with respect to proper density. So what you actually notice, there are more kind of spherically symmetric objects here because you can take all diffeomorphism invariant guys here. But those are the ones that are usually considered in spherical symmetry. You're interested in study the dynamics of those. So I mean, this comment here just means that there are various definitions of spherical symmetry, and depending on how you do it precisely, more or less degrees of freedoms are retained. I mean, these are the degrees of freedoms that people usually consider in mini-superspace or midi-superspace. Now, what about the dynamics? It's more challenging than in Bianchi 1. In particular, you need more kind of full-blown tricks of loop quantum gravity dynamics, so you need to use Tiemann's tricks and so forth to do the computations. This is ongoing work with Antonia Zipfel. We have a map of, well, classically reduced states to quantum reduced states, and it turns out that, well, the paper is not finished yet, but it turns out that you can reproduce the proper commutator at least up to large quantum number corrections, which means that you can, in a suitable regularization, preserve or get the same dynamics up to large quantum number corrections. Okay. So let me briefly conclude. We have done this reduction program, starting with a gauge as like choosing suitable coordinates as our main ingredient. We then quantized. We imposed reduction constraints. We computed their kernel. We related the observables. So what about future work? Of course, you're interested in perturbations to this Bianchi 1 model in order to make more concrete predictions for cosmology. You want to study coarse graining here, so this is a very nice example to study coarse graining, because you can, I mean, for example, here in this spherical symmetry, the kind of the simplest state that you have there is just a single Wilson loop with one kink. And on such a state, the kind of operator here will have kind of one contribution, and this is kind of the simplest thing that you can choose there. But you can, of course, or what you want to do is you want to choose arbitrarily fine spin networks and compute how the dynamics flows with respect to such a refinement. And then, in the end, you want to study, of course, physical problems like spherical collapse or also Planck stars, and kind of compute these transition amplitudes in this framework. Okay, so thank you for your attention.
For one or two questions.
So if you try this for Bianchi 9 instead of Bianchi 1, it seems everything goes through if you just use a non-coordinate basis for one forms.
Okay.
Do you agree?
I don't know. So we have to discuss it in more detail.
Okay, but then the okay, maybe we should. But then the real question is, Bianchi 9 is like a three-sphere instead of a torus. So all your loops will be contractible, and then by
yes,
the
so I mean, in case of that, or in case that you want to use, for example, like R3 or so, you would need to specify some asymptotic conditions on your diffeomorphisms. You kind of want to anchor those holonomies kind of at infinity, and
well, it's a three-sphere. It's compact, and
yes, I'm just saying, and with a three-sphere, I mean, you need to specify some conditions. Maybe you do a second point with a meter or so.
Okay, yeah, we should talk.
Yeah.
More? Okay, getting there.
All right, I'm going to ask a more general question, obviously. Going back to this interesting diagram that you drew, right?
Mm-hmm.
So how important is this quasi-periodicity observationally? I mean, do you see quasi-period or some type of modularity?
It is what separates Wheeler-de Witt from loop quantum cosmology. I mean, this measure that you have here, it's fundamentally different from Wheeler-de Witt in the sense that, well, von Neumann uniqueness doesn't apply, and you get different predictions. In particular, I mean, you do not get a Big Bang, which you get in Wheeler-de Witt. So it is of fundamental importance that you do this, that you go from AP to the exponential of P, and that you use this representation where this is not continuous, where this is not continuous.
So that's great. Okay, so you resolve something at short distance. How about the long distance?
I mean, about long. So what people have, what people have studied in loop quantum cosmology is they take some some sharply peaked wave packet and they evolve it, and well, at large times it's sharply peaked on what you have in the Wheeler de Witt. However, it only changes once you reach Planck's. Planck
So the
density.
short distance effect, the resolution is washed out, even though there is a quasi-periodicity. I know the statement you're making, right? In one case, right, Wheeler de Witt, you do have a bang, right?
Mhm.
Now you say like, okay, I'm going to do this Harrell-Bohr type of thing, right? And it's fundamental, so it resolves the bang.
Mhm.
I guess you get a bounce, right? All right. So that's great at short distance, early times. Then you say like, I propagate that,
Mhm.
and in the future, do I agree with what Wheeler de Witt would tell me, or do I depart radically?
Well, there are small departures, which Aurélien told you about on Tuesday. I mean, you want to study perturbations on the space-time and see. But they're small, yes. So I mean, what he told you is that there are scenarios, I mean, depending on the number of E-folds, that you will not see anything, and there are scenarios depending on the number of E-folds and the mass of the scalar field for inflation, where you would see a small deviation. There's no, I mean, I cannot speak for him. There is nothing universal yet. We cannot say if we don't see this tomorrow, then the theory is ruled out. No. But
this kinematical parameter, then it blows up in your face when you go to large distance. So that's why at some point you had to do some extra fudging, replacing lambda by
yes.
an observable. So and you put that because you want to avoid the fact that you see the discreteness at large scale. So, and there's no pre-justification for that, except that if you don't do it, it blows up in your face. So
well,
your answer was not
AQC,
correct.
there is this justification.
Yeah, but it's not the Bohr compactification you're doing. It's something else. That, you're fudging. You try the Bohr compactification, it doesn't work. Then you fudge afterwards to kind of cure. Right, that's what's happening in LQC.
I would disagree that. I mean,
Well, you have to choose a precise. There's no justification for the precise choice you made at the end for this lambda being dynamically dependent, except that if you don't take this particular
well,
regularization,
the argument
it
in
doesn't
AQC,
work.
I mean, the argument in AQC, which led to making it kind of one, was as far as I
Before,
understand.
it was before.
Yeah.
Okay, when you choose your lambda to be
Here. So
Yeah,
so
so
in this
that's-
case, you find if you would choose lambda equal to 1, then you would get a bad approximation for one of your operators. So it would already be ruled out here because your regularization is bad. And the statement is you need to make a regularization such that, well, this integral is approximated by this guy.
Yeah.
And then this
But
is
it's
the
no longer
simplest
really
thing.
Bohr compactification.
So I think the general point is that there's the construction and several choices in the construction are designed so to get agreement with the semi-classical Wheeler de Witt at late times and large universes, which is reasonable, but it's not coming out
Yes, but I
universal,
mean,
so-
what I want to say here, they are not out of the blue. I mean, if you say, I mean, this is bad because it's not a good regularization. And the simplest one that is proper leads to the right result. Okay.
So it's reasonable, but it's a choice that you make. Okay, more questions? More questions 1, more questions 2, more questions 3. Thank the speaker.